Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video today, I will implement LeNet 5. It's one of the classic one that came into the world and it was really super popular for such a long time. All right, let's jump into the implementation. And here is the image taken from the original paper published in 1998. So as the name indicates, LeNet 5 has 5 layers with 2 convolution and 3 fully connected layers. Every convolution layer includes 3 parts. One is convolution, then a pooling and a nonlinear activation function. Let's start with the input. LeNet accepts as input a grayscale image of 32 by 32. This is what we can see, and this is specifically taken for Mnist. And LeNet was like, when it was built originally, it was pretty much built for Mnist Data Set. So at this input level, LeNet is a 32 by 32 grayscale image, which is what it takes, and it passes through the first convolution layer with a 6 feature maps or 6 filters having a size of 5 by 5 and a stride of 1. The image dimension after this convolution layer changes to 28 by 28 by 6. And how we got these 28 by 28 from 32 by 32, that is pure arithmetic of the convolution layer. That is, you start with 32 and you deduct 5, because 5 is a filter size or the kernel size, and add plus 1. So 32 minus 5 plus 1 will give you 28. That's how this size is arrived. And then look at, so in this image down below here on the right side, I have actually enlarged what's happening under the hood for the convolution conv2d layer only. So let's say input image 2, which is 32 by 32 by 1, and then I apply the conv2d number of filters, which is also the output channels or the number of output channels, which is this number 6. I have the filter size of 5 by 5, and padding has been defined to be 0 here, and stride also has been set at number 1. So when so during the conv2d, the total trainable parameters will be this total weights plus bias, because y equal to wx plus bias, and the total weights will be number of filters into number of filters, that is 5 by 5, and then I have to also multiply the input channels and output channels. My input channel is 1, output channel is 6, so this total multiplication, to that I have to add the bias term, which is 6. And by this multiplication and addition, I get 1, 5, 6 as a total number of trainable weights. And what will be the number of connections? That will be the size of the output of these operation multiplied by these trainable weights. So my output size becomes 28 by 28. So total number of connections will be 28 multiplied by 28 multiplied by 156, which is 122,304. This is for the first layer, conv2d. And after this convolution, LeNet 5 applies a subsampling. And what exactly is subsampling? That's just your mean pooling or max pooling, that is average pooling or max pooling. So subsampling is pretty much this. You have a 4x4 matrix that you take the average of these 4x4 and that becomes a single cell. That is your output matrix. That's your average pooling. And in this case, if I apply max pooling, then I have the input as 4x4 pixel of matrix, and I take the maximum value out of these 4 numbers, and output will be the max value. That will be a single cell. So basically, your 4x4, each 4x4 matrix from here, that is before applying subsampling or the average pooling, will become 2x2. That is, you very much half it, and that's why in the second layer, that is in the subsampling layer, you start with 6 by 28 by 28 input shape, and your output will be 6 by 14 by 14, because you apply these subsampling where your the pooling number is 2 here. That is, you for each 2 by 2 matrix will become 1 by 1, halving it, and that's how you get from 28 by 28 to 14 by 14 after applying the subsampling. Next, I have a second convolution here with 16 feature maps having size of 5 by 5 as the filter size or kernel size and a stride of 1. In this layer, only 10 out of 16 feature maps are connected to 6 feature maps of the previous layer. The main reason for this is to break the symmetry in the network and also keeping the number of connections within reasonable bounds. And after that, I have the fourth layer, which is again an average pooling or max pooling layer defined as subsampling here. So in here, the filter size is 2 by 2 and a stride of 2. And this layer is the same as the second subsampling layer, except that it has 16 feature maps so that the output will be reduced to 5 by 5 by 16. And the fifth layer is a fully connected convolution layer with 120 feature maps of each of size 1 by 1, and each of these 120 units or 120 neuron in C5, that is layer 5, is connected to all the 400 nodes in the previous layer. And how do I get 400? Because the previous layer had an output of 5 by 5 by 16, giving me 400. And so in this fifth layer, and that is the fully connected layer, the trainable parameters total will be weight plus bias, which is my weight will be 400 into 120, and bias is also 120, giving me 48,120 as a total trainable parameters. And after these, I will have the next layer, the sixth layer. This is also a fully connected layer with 84 units as output channel. So from the previous layer, I get these trainable parameters, which was 48,120. And then after this layer, I will get the trainable parameters of the sixth layer will be again weight plus bias, which will be 120 multiplied by 84 plus 84 bias, giving me 10,164 total number of parameters. And finally, there is a fully connected softmax output layer with 10 possible values corresponding to the 10 digits of 0 to 9 of Mnist Data Set. Remember again, LeNet 5 was specifically designed for Mnist Data Set, and that's why for the output layer I have 10 classes. And again, these parameters is coming from the previous layer. There was 84 of them, and total trainable parameters is 10,164 here again. And now that we understood the architecture, coming back to our VS Code for implementing them on the same architecture in PyTorch. So in the initial cell, it's just a normal imports, and specifically to mention that I'm importing Torch Vision. From here, I will get my Mnist Data Set. And also I'm setting the device to use if CUDA compatible GPU is available to use that, otherwise it will use CPU. And now, so to build the architecture in the LeNet, there are two sections in the function that with which I will have the architecture implemented. And those two sections are first initializing all the layers, and that is all these layers of LeNet in our underscore init method. And then there will be a function or method called forward, which will implement the sequence of the layers, and that is a sequence that they will be processed. And I'm also defining two small variables, batch size to remain at 64, number of classes 10, because Mnist has 10 classes. All right, and this is that function, that class indeed, LeNet 5. And so we can just go layer by layer with matching with the original image from the paper, the LeNet 5 paper. So first, my convolution layer here, which is this line, that is nn.conv2d. So again, like I said, that I have two methods within this LeNet 5 class. One is underscore init, and then the forward. And all my convolutions will be defined in these underscore init method. And the first layer is this convolution layer, where I have the input is a 3232 grayscale image, which passes through the first convolution layer, that is this one, with 6 feature maps or filters having a size of 5 by 5, that is the kernel size is 5 by 5 and stride of 1. The image dimension that is changes from 32 by 32 by 1 to 28 by 28 by 6. So this line implements that nn.conf2d in channels number 1, because I have 32 by 1. And here the number of channels are 1. It's a grayscale image. Output channel is 6 because I have the depth increase for these after this convolution. Kernel size 5 by 5, 5 comma 5. I could actually just mention kernel size equal to 5. That would have been just fine. But here I'm just being explicit, so I am giving it a tuple. But because it's a square matrix, if I just put kernel size equal to single integer 5, that would be very much all right. Similarly for stride, it's a tuple because stride is 1 by 1. Again, I could just give the number 1. Padding is also 0 comma 0 as a tuple. And again, for this one as well, because it's just 0, it's a square matrix, I could just give single number 0. So that's my layer 1. And then I'm getting a batch norm 2D, and then because I have output channel 6, I'm giving it this argument 6. Then a ReLU. Now this is important. In the original paper, when it was published in 1998, I guess, then the ReLU was pretty much did not come into the world of deep learning. So then they used to use sigmoid, simple sigmoid. But here now, normally for implementing LeNet 5, ReLU is used. So that's why I'm bringing in a ReLU here. And then this is my layer 2, that is which is from the picture, from the image, this subsampling layer, where either you have to do average pooling or max pooling. I'm doing a max pooling 2D. Kernel size is 2 by 2, stride is 2. This is my layer. And like I mentioned before, that max pooling will take, it will halve the overall dimension, because it is taking a 2 by 2, because its kernel size is 2. That means it will take a 2 by 2 matrix, take the maximum pixel of that 2 by 2 matrix, and the output will be a single matrix, which is a maximum value from that 2 by 2 matrix. And after these convolution layer, the next comes another convolution conv2d layer, which is this line. Okay, so self.layer2 equal to nn.sequential. This line conv2d, this is my layer 3. And so here in this convolution layer, there are 16 feature maps having a size of 5 by 5 and a stride of 1. And in this layer, only 10 out of 16 feature maps are connected to 6 feature maps of the previous layer. We talked about this during the explanation of architecture. And then again, a batch normalization, another ReLU, and to that, this is my layer 4, max pool 2D. If you match it with the image, this is the second subsampling. So which could be either average pooling or max pooling, and I'm using max pooling. And kernel size is 2 by 2, stride is 2 by 2. And after these second convolution layer, I will have my next layer, which is my layer 5 here. So this fifth layer is a fully connected convolutional layer with 120 feature maps, each of size 1 by 1, and each of the 120 units in this layer is connected to all the 400 nodes in the previous layer. And how I'm getting the 400? It's because 5 by 5 by 16. That's how the previous layer nodes will be calculated. And after these layer 5, I will have another ReLU. Then again my layer 6. And this is my second fully connected layer, and with 84 units here. And after this, I will have another ReLU. And you can just, while I'm doing this, you can just match it with this image. So here goes my 120 vector fully connected layer. Then my F6 is, that is layer 6 is 84 vector. It is again a fully connected one, which is this one. And then finally this fully connected layer FC2, which is the final layer, a fully connected layer. And here that will have the output channel, that is out channel, so it will be the number of classes, that is 10, because I will have 10 possible values corresponding to the 10 digits of Mnist. And it's taking the in channels as 84 because that's what it is getting from the previous layer. And after the underscore init method, I have to define the forward method. So quick words on the fundamentals of forward method, that what exactly does this forward function outputs in a PyTorch neural network. So this forward method, you are pretty much creating the logic of your forward pass. In a very simple use case, you just call all created layers one by one, passing the output of one layer to the next. That's what exactly I'm doing here. That is output. It takes an input value x, then that becomes my first input value for the first output, that is self.layer1, and to that layer 1 I'm passing x. Then this output again is passed to the layer 2, and the output of that is held in this variable output again. And similarly, if all the layers it goes on like this, that is, I'm updating this output variable by taking it forward layer by layer. So in other words, the forward function computes the matrix multiplication of the weight tensor with the input tensor, and then does it again and again for each of the layer. So in this case, where the training data set are images, the forward function passes the image through the model, that is forward pass, and applies the operations previously defined in my network, and that means in my underscore init method. So that's exactly what I'm doing in the forward, that each of these layer that has been defined here, layer 1, layer 2, FC, FC1, FC2, all of them will be invoked one by one here. So first layer 1, then layer 2, then fully connected FC, then my ReLU. You can just compare it with the underscore init method, and you will see exact sequence are maintained. So FC, then ReLU, then FC1, then another ReLU 1, and then FC2, and finally return these output. And that's my final output from my LeNet 5. And now, before I move on to the next cell, two points to explain here. The first one is in the forward method, after my second convolution layer was applied here, that is layer 1 and then layer 2, then I did a reshape of my output variable. And why exactly I did that? And the reason is, so to understand that, first I printed, just print the output layer before doing this reshape, and then also print the output layer after doing this reshape. So let's look at what I got before the reshape. So before the reshape, when I printed this line here, let's zoom in a little bit. When I printed these output here, I got a torch.size of 32 by 16 by 5 by 5. And after the reshape, I got the same variable reshaped as torch.size 32 by 400. Now, why is it that? And the reason is that in PyTorch, images are represented as channel, height, width. So a color image will be represented something like this. Just for an example, 3 channels, for example, 256 by another 256 to represent height and width. And during the training, that is, this forward method is actually executing a training. So during this training, you will also get another dimension to this dimension list. That is your number of batches. So during the training, your dimension will take the form of batch size, channels, height, and width. So before these 3 will come the batch size. And in our case, what is the batch size? I think we defined it at 64, and that was actually getting modified after layer 2 with the application of the subsampling, with application of the computation here, I guess. Here in this layer. So I got these 32 number as a batch size, and that's actually representing the batch size. So that means that before applying the reshape, I have this output variable output tensor indeed, shaped as 32 batches, 16 channels, 5 height and 5 height. Sorry, the last one is not height, it's width. So I have 32 as my batch size, 16 channel, 5 height, and then the last fifth is the width. So this is a 4-dimensional tensor before applying the reshape. But before I could apply the fully connected layer, let's go back to the image. The first fully connected layer is here. And so before applying the fully connected layer, I have to convert this 4-dimensional tensor to a 2-dimensional tensor. Now, why? Because the fully connected layer will have an output shape of 400, and that's a vector. And so for the reshape, I cannot definitely change the batch size. I have to keep it as it is. So I can change the other dimension, and that's why in the reshape I am passing the batch size as it is, output.size 0, which will return 32. So if you just print output.size 0, because output.size is this this list over here, so 0th element is a 32, that I'm keeping here as it is, and I'm giving -1, which is I'm pretty much telling PyTorch that decide it or infer it given the first dimension. And after PyTorch did this calculation, the second dimension will be inferred, and that will come out to be 400. So, and that's why after the reshape, when I'm printing the same output variable, I'm getting a torch.size 32, which is the number of batches, and then 400 as the second dimension. And then this output variable is fully ready to be applied to the fully connected layer here. So that was the reason behind doing this reshape, and you will find this kind of reshaping happening in forward very often. Because in most of the network, while you move forward from layer to layer, at some point you have to reshape your variable, your input tensor, before you can pass it through the next layer, because there will be a dimension mismatch, and to make it pass through from one layer to another layer, you have to make the dimensions compatible. And then the next question that may come to your mind, that where is my softmax over here? And that is as the output from the last layer of your neural network. You probably are thinking that you should get a softmax somewhere, but you don't see it here, and that's because when in our next cell, I'll be applying cross entropy loss. That is this neural network that I built over here, that will be taken through a cross entropy loss, and our softmax is included right within this, because in PyTorch the nn.cross entropy loss function is handled the softmax computation, which of course works with the raw output of your last layer of your neural network. So with that, my network and the architecture is completely built. It was actually very simple, and now I have to test it on the Mnist data set, and for that I have to first get the data set. And a quick word on the Mnist data set, probably all of us already know that this is the images are grayscale, all of which are size 28 by 28 and composed of 60,000 training images and 10,000 testing images. And I will get this data set using torchvision.dataset module. So first I'm getting the train data set. So you are using torchvision.datasets.mnist. You have to mention the path where this dataset will be downloaded in your local machine or in your cloud machine. Train equal to true means the 60,000 training samples will be downloaded. And transform, this is important. I am doing some basic transformation on the training dataset. The first one is resize to 32 by 32 because the original Mnist dataset are all 28 by 28. I cannot input that into my LeNet 5 because, like you see, that it takes a 32 by 32 input images as the first input layer. And that's the reason I'm doing a resizing transformation for all the dataset into 32 by 32. And then the rest of these two transformation is pretty standard. I am converting to tensor with the two tensor method, and I'm also scaling the dataset with normalize. I'm passing mean and standard deviation. Download equal to true. This means that if the dataset is not already downloaded, it will be downloaded, and if it is there already in this path, then it will not be downloaded. Again, and exactly the same kind of code for test data set, only change is train equal to false here. And then I am getting my data loader. So for that I'm using torch.utils.data.data loader. Very standard code. You will see this code everywhere in all PyTorch vision, computer vision or image processing projects. So this will data loader will control my the input to the training function of my training images, and a data set is my train data set. Batch size I'm keeping it at whatever I have defined at the top. I think it was 64. Shuffle equal to true. Exactly the same for test data set data loader as well. And now we're defining learning rate to be 0.001. Then just with the single code, I am creating the model object, model instance. So model equal to init 5, that will take the number of classes, because remember when defining this function, the argument was number of classes here, which is 10 in our case. And I'm transferring to device. Our device has been defined to be GPU, and if that's not available, then CPU. Criteria, that is loss function, because it's a multi-class classification problem. Obviously I'm using cross entropy loss. Optimizer, setting the optimizer with the model parameters. So torch.optim, I'm using Adam optimizer. Learning rate remains to be 0.001, and total step will be just the length of the train data loader. And now I'm just printing these length of train and test data loader, 938 and 157. Yes, remember this why 938 157, because the total data set is divided into batches, and that's why it will the data loader will give me batch by batch data, and that's why I'm getting the length of that is as 938 here. And then finally the training method. Again, very simple code here, and very standard, and only the simplest steps I have taken, no complexities here at all. So the train method takes a model criterion, that is a loss function, optimizer, num epochs, by default it's 10. Total training loss is an array that will be updated during my training, and total steps has been defined to be length of the train data loader. Now there will be two loops. One will be running for each epoch, and within each epoch I will be looping through the train data loader on a batch by batch basis. So within epoch I am defining this running loss. This running loss will continue to be updated when the batch loss is calculated. And then within this epoch I have the second inner loop for enumerating through the train data loaders, and while enumerating I will get the index and also the tuple which will contain images and labels. And both of them I have got to transfer to device, because all these tensors need to remain on the same hardware, else you will get some problem. And then the next one, just outputs. For the outputs I am only taking the model, passing it the images, and that will give me my outputs. And loss is calculated as criteria, outputs and labels. That is, this output is my predicted variable and labels is my actual ground truth. When I pass these two arguments to my criteria, which is nn.cross entropy, that will give me the loss. And after calculating the loss I have to do the backward propagation as well. So optimizer.0grad, very standard steps here that I'm following. So this will clear the past gradient by setting the gradients to 0 before every update. Then loss.backward, it will calculate the new gradients, and then I'm updating this running loss. Now that my loss is already calculated, I am adding these loss.items to my running loss. So this actually become my accumulated running loss. And then I'm multiplying with image.size0. Let's understand why exactly I'm doing in this line. First, note that I'm taking loss.item and not just loss, because this variable loss that is returned from the criteria, that is nn.cross entropy, is a grad function. It is not a float Python value. So I have to get the actual scalar float Python value from this loss, and that's what this loss.item does. And then I have to multiply that with the image.size0. This is actually the number of batches Remember, images is coming from this loop, this iteration. I'm enumerating over train data loader, and these images will have the number of batches in its size array. So because and I have to do this multiplication because this loss is an average loss, just following the PyTorch way of calculating the loss. It is the average loss or loss of this batch. So to get the total batch loss, I have to multiply this loss by the number of samples in the batch, which is what I get from images.size 0. This will give the size, and the 0th element will give me the total number of samples. And that, if you multiply with the loss.item, you will get the total running loss for the batch. And that's how I'm updating the running loss here. Optimizer.step will just update the weights. It's a standard way of applying PyTorch's backward propagation. And in this line, I'm just printing when the epochs is running, I'm just printing intermediate result. This is not that important, but the next two line is very important again. So epoch loss, after these batches are run, then I'm getting the epoch loss. That will be my total running loss, which is accumulated total running loss divided by length of the train data loader. So basically, this running loss is an unaveraged amount. So outside this batch loop, that is outside this inner loop, which is for the batches, what I'm doing is divide these accumulated unaveraged batch loss represented by this running loss variable by the length of my train data loader to get my epoch loss here in this line. And then after I get my epoch loss, I just want to keep track of this epoch loss, because at the end I want to do a plotting where I want to show that how my loss is reducing when I'm going through various epochs. So I want to keep account. I want to keep the actual loss for each epoch, and so that's why I've already defined this total training loss at the top. To this list, I will be appending these each epoch loss. And finally, from this train function, I am just returning the total training loss. And then I just have to invoke this function in the next cell. So that's what I'm doing. Train, then to that I'm passing my model, which has already been defined, criteria, optimizer, a number of epochs. Actually, initially I was training for 3 to just check that it's working, and then I trained for 30. So that pretty much all you have to do to get the result. Now I ran this in my Colab, so let's go to my Google Colab and check the result. And here I am in my Google Colab, and so here when I ran this cell, it will do all the 30 epochs of training. And as you can say, with each epoch my loss is gradually reducing. And after the training was done, when I just printed the total training loss, which is the output from this function, that is a train, because it will give me the return value as a list that contains all the losses of all the epochs. And that will be just like this. That is, for my first epoch, this was the loss value. Then it continues to increase throughout the epoch. And finally, I have to just plot it with matplotlib. I'm plotting only my training loss, and as you can see, on the x-axis I have epoch, on the vertical axis I have losses, and it continues to increase over the 30 epochs. I stopped at 30 epoch because here my purpose was to test the architecture is working, but looks like even at 30 the loss was reducing, so I could have gone probably another I don't know, 30, 40, 50 epochs to see even much better result. So overall looks like that this pretty much worked well, this LeNet 5. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.